syllabus of electronic devices, if we go, we have energy bands in intrinsic and extrinsic semiconductors, correct or not, dear students? And also we have equilibrium concentration of carriers, and we have EK diagram, which is direct band gap, indirect band gap semiconductors. Then we have the carrier transport, which is so called as a diffusion, drift, mobility, recombinations, whatnot, resistivity. And you have generation, recombination of carriers, and we have a PN junction, Zener diode, bipolar junction transistor, and you have MOS. You don't have JFET in your syllabus, please take care of that. So don't spend time to prepare for JFET, okay? What exactly you have in the syllabus, I appeal everybody in the class, concentrate more on that. What is not in your syllabus, don't do any sort of work on that, okay? And you have optoelectronics, light emitting diodes, photodiodes, and a solar cell, no laser part and all the things, okay? So, what I do, what I suggest everybody in the class, what I suggest here is divide the entire syllabus into 4. For example, the very first, I can say, you can move towards electric field profile. The very first part of entire syllabus, electric field profile. Sir, what I learned from electric field profile? What did I learn from electric field profile? The very first thing is, if you think about electric field profile, let me go with the PN junction. Okay, I have a PN junction diode, or a BJT, or a MOSFET. Whatever may be the case, you have a PN junction. Whenever you think about a PN junction, there exists a built-in electric field. Correct or not, dear students, right? So you have a PN junction. So it is P type, it is N type. So here I have negative ions, and here I will be having, what, dear students, positive ions. So there exists an electric field, which is so called a built-in electric field. And if electric field is moving from positive to negative, there exists a force acting in opposite direction with respect to electrons' point of view. As I discussed a number of times in the class, follow only the force of electrons. No need to go with the holes, okay? So this is the force direction acting on electrons. Of course, so called built-in force. So when you think about, when you hear the word electric field profile in the entire syllabus, the very first thing is you should recollect the concept of a junction electric field. So you should understand, the idea behind the junction electric field and built-in force, whatnot. After that, you need to go for the Poisson's equation, because due to this electric field, you will be getting electric field profile, you will be getting a voltage profile, you will be getting a charge density profile. For example, Poisson's equation, del square V is equals to minus integration rho V by epsilon dx. I'm sorry, minus rho V by epsilon. Am I right here? Minus rho V by epsilon. Excuse me, correct, dear students, right? So why should I go for Poisson's equation? Because it has space charges. In the depletion region, we have space charges. I mean to say, this is like space charge region, or we say transition region, correct or not? Depletion region. So because of the space charges, and because of the capacitance nature, because p-type semiconductor, this entire portion will act as a plate, and this is second plate. Two plates separated by dielectric material. Yes, I have a capacitance. So because of the capacitance, because of the space charges, I can simply use the concept of a Poisson's equation. So-called rho V is nothing but a volumetric space charge density, or a volumetric charge density. Am I right here? So from this Poisson's equation, you can easily find the electric field. What is electric field? So electric field is simply nothing but minus del V. True or not? Or simply minus dV by dx. So from here, you will be getting, integration rho V by epsilon dx. Because del V is nothing but what here? Minus integration rho V by epsilon. You will be getting electric field there. So if I want to get an electric field profile, any question in the exam, if I want to get electric field profile, I should know the charge density profile. Integration of that charge density profile, you will be getting electric field profile. So whatever may be the question, if any examiner is asking you to draw the electric field profile, okay, just try to go with the charge density profile, the shape what you're going to get, the charge density profile, then go for integration. For example, if the charge density profile is like a square wave, it is like a square, okay, then integration of that will be like a triangle. Excuse me, right? If the charge density profile is like a curvature, integration will also be like a curvature. And if it is charge density profile is positive, electric field profile need to be also positive. In that way, you are supposed to decode, which is very important. From electric field profile, you can easily produce what here? Voltage profile. Guys, okay? So because of that voltage profile, I can easily go with, built-in voltage. I can easily go with the junction voltage. Then what else we learned from electric field profile? Just recollect. From electric field profile, you can easily find the breakdown voltage. You know that? The relation between breakdown voltage and doping concentration. What is that? Breakdown voltage is inversely proportional to the doping concentration. Higher the doping, lesser will be the breakdown voltage. That relation is very, very, very important. That is I got from electric field profile. And from electric field profile, you can easily measure the depletion width of the semiconductor junctions or space charge regions. You can easily measure the depletion width. Higher the doping, lesser will be the depletion width. That formulae you're going to get. For example, depletion width of a PN junction, if you ask me, under root 2 epsilon by Q, 1 by Na plus 1 by Nd, or 1 by Na plus 1 by Nd into the contact potential. That is for a step graded. Excuse me, correct or not, dear students, right? Just try to recollect, please. My humble appeal is repeat the subject, which is very important. Recollect the concepts, which is very important. And, after that, what we have learned from electric field profile, the MOSFET. The MOSFET threshold voltage. You can easily measure the threshold voltage from electric field profile only. If you want to find the electric, threshold voltage of a MOS diode, practically speaking MOS diode, that means the minimum voltage required to produce a channel. The minimum voltage required to produce a channel is a threshold voltage. If I want to find that threshold voltage, no choice you have. You must go for electric field profile only. Threshold voltage, hope you remembered. If I say NMOS, okay, what is the formula? Under root 2Q, epsilon silicon, Na, that is nothing but substrate doping, into Xi silicon, which is the potential in the semiconductor by Cox dash. That means oxide capacitance per unit area plus Xi silicon, where Xi silicon must be at least equals to 2 times phi f. What is phi f? Fermi potential. Am I right, dear students? So then only you'll be getting threshold voltage. Of course, if I go for the practical MOSFET or a practical MOS diode, then you're supposed to experience some sort of traps, some sort of charges in the oxide, which is nothing but a Q dash oxide or a Q dash SS, which is nothing but minus Q oxide by Cox dash. You'll be getting different formulas, right? Everything we got because of the electric field profile. Not only that, if you think about again electric field profile, you need to understand about capacitance. Correct or not? So capacitance of a MOSFET, capacitance of a MOS diode, capacitance of a BJT, capacitance of a PN junction diode, charge storage capacitance, space charge capacitance, am I right? Junction capacitance, transition capacitance, diffusion capacitance, depletion capacitance, whatnot. If you want to find that, I need electric field profiles. No other choice I have. Why should I study about capacitance? I can use the semiconductor as a voltage variable capacitor. The best example is a varactor diode. I can use it as a voltage variable capacitor. And because of the junction capacitance what I have, it may be a BJT or it may be a MOSFET. There is a very huge limitation of using my devices at a high frequency response. At high frequencies, gain decreases. I hope you know from analog circuits, which is a design course. Am I right, dears? So whenever frequency increasing, the gain is getting decreased. It may be a MOSFET or it may be a bipolar junction transistor because of the capacitance what I have at the junction. Am I right? Not only that, there exists some time delay behavior, transient time. If you want to find the transit time, transient behavior, or a transit time of a BJT, or a transit time of a MOSFET, or a transition frequency, Ft is equals to 1 by 2 pi tau t. Am I right? If I want to find that, no other choice. I need capacitance, and for that, I need electric field profiles. So try to interconnect the concepts what we have studied. So for your notes purpose, I'm giving here, I think this will help you like anything because you are very near to the exam. So if I write everything on the board, I think that will be the time waste. This is not the time to do research. This is the time to implement. Okay, not for the research, just for implementation. You are very near to the exam. You are entering into the war, the battlefield. Just throw the arrow, man. Don't do research. Okay, now go with that. So what is first? What you should understand from electric field profile, the Poisson's relation, what we have. Then electric field profiles. Then we have a voltage profile. Then by electric field profile, we can easily get relation between electric field and doping concentrations. And also from electric field profile, we can find the depletion width. From electric field profile, we can find relation between breakdown voltage and a doping concentration. You know that, right? So like epsilon into E critical whole square. E critical is the electric field at which there exists breakdown. Epsilon into E critical whole square by 2Q light doping device or light doping region, 2QND or 2QNA. Am I right, dears? You please recollect. And also, we can find the capacitance of a diode. It may be a charge storage capacitance, voltage variable capacitance. There exists a time delay, a transit time, transition frequency, whatnot. In the similar way, we can find threshold voltage of your MOSFET from electric field profile. And also we can find the shape or a slope of energy band diagram, which is very important. So what shape exactly we're getting in energy band diagram? Exact opposite, 180 degrees out of phase, you'll be getting with the voltage profile, where I discussed a lot of examples in the class. Correct or not, dear students, right? And also most of the MOS capacitance behavior, maybe accumulation mode of operation, depletion mode of operation, inversion mode of operation, you'll be getting from electric field profiles. So if you hear the word electric field, you need to just recollect everything. Everything must come into the mind. That is very important. Am I right here? The second, energy band diagram. This is the second, the entire syllabus of your, electronic devices. The first, electric field profile. What we learn from electric field profile, why it is important, we have seen. Of course, I'll go in very detail and we'll be discussing some numerical part for your revision series. Is it okay? And energy band diagram. So what we get from energy band diagram, very interesting thing, dear. So if I want to find the kinetic energy of a particle, if I want to find the potential energy of a particle, maybe a free electron, maybe a hole, I need energy band diagram. If I want to understand how much energy I should provide to break the covalent bond, how much energy I'm supposed to give externally, yes, I need energy band diagram. If I want to understand, how many electrons per unit volume, so-called electron density or concentration of electrons participating in the current, if I want to measure, I need energy band diagram. If I want to find hole density in the valence band, yes, I need to find energy band diagram. If I want to understand the generation of carriers, recombination of carriers, I need energy band diagram. Recombination, for example, if a free electron from the conduction band directly recombining with the holes in the valence band, I repeat, free electrons in the conduction band directly recombining with the holes in the valence band, it is called band to band recombination. Am I right? Or practically speaking, there existed traps, dislocations, unwanted impurities. They are not wanted, they are unwanted impurities. If you're experiencing any sort of traps or if you're experiencing any sort of unwanted impurities, then there will be no band to band recombination. So there exists a huge, energy states, correct or not? For example, if it is EC and if it is EV, I understand there exists a huge energy states in between. So once a free electron want to recombine with the holes in the valence band, electrons in the conduction band, if they want to recombine with the holes in the valence band, in the middle, they could experience some recombinations, or from the trap states. These are all called what here? Trap energy levels or trap states. From these energy levels itself, you make it a new generation of carriers. In that aspect, then there will be no band-to-band recombination. Then, as I discussed already, the scientists who had done a lot of research on this is Shockley, Reed, and Hall, SRH recombination. The recombination, rate U is equals to N dot P minus Ni square by N plus P plus 2Ni into 1 by tau. Tau, of course, you know that it's a lifetime, right? That SRH recombination, if you want to understand that, I need energy band diagram. If you want to understand band-to-band recombination, yes, I need an energy band diagram. Guys, I hope you're getting the points, right? In the similar way, when a free electron recombining with the hole, electrons in the conduction band, if it is recombined with the holes in the valence band, so-called band-to-band, under momentum difference is 0. EK diagram, y-axis energy, x-axis momentum. So under EK, with the momentum difference is almost equals to 0. If you're experiencing any recombination, you'll be getting like this, right? So you'll be getting like this. X-axis, momentum, k vector, and y-axis, energy. So if electron in the conduction band directly recombining with the holes in the valence band, under momentum difference almost negligible, then the energy what it is releasing, that energy is nothing but a light, so-called photo generation. Then that recombination is called a radiative recombination. And I hope this is very important for light emitting diodes. This is very important for optoelectronic devices, laser diodes. Therefore, these are called direct band gap semiconductors. Maybe a gallium arsenide, indium gallium arsenide in gas, aluminum nitride. The material with a huge energy gap, aluminum nitride, 6.1 electron volt, I hope you remembered. Similarly, in GaN, indium gallium nitride, the best example is a white LED or a blue LED. GaN, gallium nitride, again it's almost like a white LED, 3.6 electron volt you'll be getting almost, right? We discussed a lot and I asked many questions in the class, I hope you remembered, right, dear students. And so this will be coming under what here? Direct band gap semiconductor. So whereas if the recombination, you have some, momentum difference. For example, I say if, conduction band is here, valence band is here, the EK diagram is in this way, such that electron recombining with the hole in this way, then the energy what it is getting released, that is not photons, that is what it phonons. So they are responsible for heat energy, not light energy. Yes, correct or not, dear students, right? So if I want to find that EK diagram analysis, no other choice you have, you must go for energy band diagram. In the similar way, if I want to find, what exactly the average energy, when a particle is participating in the current, it may be electrons or it may be holes. I'm getting some current in the device, maybe N type, maybe P type, maybe BJT. If I want to find the average energy acting on the particle, then no doubt I need a Fermi energy levels. I need what here? Fermi energy levels. If I want to understand whether my device is under equilibrium or a non-equilibrium, yes, again I need the concept of Fermi energy levels. For understanding that Fermi energy level, I need energy band diagram. Guys, okay, so the entire picture of electronic devices or VLSI fabrication tomorrow, if you go for the post-graduation programs, it may be a manufacturing part, a design part, or a manufacturing front end or a back end. You're supposed to go for energy band diagrams, which are very important. Maybe a homo junction, maybe a hetero junction. I need energy band diagrams. So the entire electronic devices, the second part where we divide, that is energy band diagram. So if you check it out for your notes purpose, guys. So the first point, why should I study energy band diagram? If I want to understand the kinetic energy and potential energy of the particle, or to understand the strength of the covalent bond, I need to go for energy band diagram. In the similar way, to find built-in voltage or to find the contact potential or a junction potential, which we can easily get the diode voltage. This is the diode voltage. I need energy band diagram. In a similar way, to understand how carrier transport exists, like drift, diffusion, and tunneling phenomenon, yes, I need energy band diagram. In the similar way, to justify the breakdown mechanism, maybe avalanche breakdown, maybe a Zener breakdown, if I want to justify that, how the carriers are getting multiplied, M is a multiplication factor. Excuse me, right here, what is M? M is equals to 1 by 1 minus, diode voltage by breakdown voltage whole power N, where N is an empirical constant from value 2 to 6. Most probably 2 to 6 the range will be, right? So just recollect from the breakdown concept, and we discussed a lot, that is through energy band diagram. And to understand state of a device, whether it is under equilibrium or a non-equilibrium or a quasi-equilibrium, I need a Fermi levels. No doubt for that purpose I need energy band diagram. And to understand EK diagram, energy versus vector, K vector, which is nothing but what here, EK diagram. So I need energy band diagram. And to understand generation and recombination of carriers, that generation and recombination of carriers just now I discussed. So if I want to find that, I need what here, energy band diagram. And if you want to get a high clarity about the Fermi energy levels, I need energy band diagram. So if you just think about energy band diagram, I think more 50 to 60% of entire syllabus, it is strictly depends on this energy band diagram. 60% of your syllabus. Guys, okay, so please take care of that. Especially the people who are going for a back end or a front end engineering, they need this energy band analysis, which is very, very, very important under electronic devices, or we say semiconductor devices. Now the third part of your entire syllabus of electronic devices, I am going with a carrier transport and current equations. When you think about the carrier transport, your mind should start thinking, man, your mind such, it must be having a beautiful encyclopedia, right? It's filled with a lot of content. So, if you think about a carrier transport, what carrier transports we have studied here in our syllabus? The first is drift. When you think about it, drift, what something come into the mind? The first is mobility. Drift strictly depends on mobility. Drift strictly depends on concentration of carriers. Okay, concentration of carriers. So mobility is very important. Conductivity calculations are very important. It may be intrinsic conductivity, maybe N-type conductivity, maybe P-type conductivity, maybe extrinsic conductivity. Am I right? And how conductivity is changing with respect to temperature, how mobility is changing with respect to temperature, how mobility is changing with respect to doping, how mobility is changing with respect to electric field, what are the units of mobility, everything you need. So think about a drift, okay? Then the second transport, what we have is a diffusion. When you think about a diffusion, the very first important thing you should recollect is what here? Concentration gradient of the charge carriers. Concentration gradient. It strictly depends on concentration gradient, strictly depends on a Fick's law. Drift depends on Ohm's law. Diffusion depends on a Fick's law. Am I right? Precisely speaking, Fick's first law. right? And diffusion, I need a concentration gradient of carriers, and diffusion coefficient is very important. And if I want to find the built-in electric field, if I want to understand the way how electric field exists at the junction, diffusion is must. If I want to go for a carrier transport equation, diffusion is must, right? Everybody in the class. So yes, that is the second transport I can say. And diffusion is independent on electric field, don't forget about that. And you have recombination. For a proper diffusion of charge carriers, you need a recombination. Then in diffusion, what formulas are very important? Diffusion current formula is important. Then Einstein's relation you have, that is under equilibrium or a quasi-equilibrium, d by mu is equals to kT by q, or a thermal voltage, which is very important. And next, what is important is, at equilibrium, how drift balancing the diffusion such that total current equals to 0. Yes, that is important. That is so-called equilibrium electron transport equation, equilibrium hole transport equation. Drift plus diffusion is equals to 0. Yes, try to recollect. In the similar way, you have tunneling transport. Of course, you may not be having tunnel diodes in our syllabus, but you have a tunneling mechanism in the Zener diode, which is so-called as a Zener breakdown. Zener breakdown strictly depends on tunneling, correct or not? So tunneling transport is very important, right? And the thermoelectric currents you have, which is, which may responsible to create noise, thermal noise, which is not advisable in our communication systems under devices, okay? So it is not at all advisable. So thermoelectric currents, that transport is very important. Then you should understand about equilibrium, non-equilibrium, thermal equilibrium, steady state, whatnot. Excuse me, right? Please recollect here. It's a beautiful subject here. Please understand my words, okay? And what else you have? Currents, a diode current. If I want to go with the diode current or a transistor current, we discussed a lot with the concept called a low level injection. You have two types of injections, right? One is a low level, other is a high level injection. For the best example is amplifier, analog devices. If I go amplifier, which is a basic part of analog circuit, maybe op amp or maybe BJT or MOSFET. So if I go with an amplifier, no doubt low level injections are must mandatory. And we are dealing with the low power electronic devices, not high power electronic devices. So most of our applications, it may be a clipper, maybe a clamper, maybe a rectifier, whatever applications you go, you have a low level injection. So we studied a lot about low level injections. So in low level injections, what parts we have covered? Steady state we have covered, equilibrium, non-equilibrium, correct or not, dear students, right? After how much time the carriers are reaching towards the steady state, and how the concentration of carriers changing with respect to time. For example, minority concentration Pn of t is equals to Pn naught plus GL tau p into exponential minus t by tau p. Correct or not? Or Pn of x is equals to Pn naught plus delta p into exponential minus t minus x by Lp, right? So which is so-called minority concentration or excess concentration of carriers. When you think about excess concentration, you need to go with the quasi-equilibrium, which is very important. Difference in the Fermi levels, Fn minus Fp. Fn and Fp represents quasi-Fermi levels. You'll be getting that. So, the currents are very important, strictly depends on the low level injections. Then a practical current, ideal current. Practical current equation, for example, if I say diode equation, I is equals to I naught exponential diode voltage by Vt minus 1. Whereas, if it is practical, you are supposed to include traps. So, in the denominator, eta need to be included, am I right? So, that's it. So, that's a diode current equation. The same, you are supposed to implement for a bipolar junction transistor, maybe common emitter, maybe common base. Emitter junction must be always forward bias if you are expecting any transistor to be closed. Excuse me, right, dear students? So, the same expression of diode, which is so-called as a law of junction, because diode currents strictly depends on what, dear? Law of junction. I repeat, law of junction. Based on that, you'll be getting the BJT, you'll be getting the diode. That's why the semiconductor devices whose currents are obeying the law of junction, they are called as a junction devices. If it is a diode, junction diode. If it is a transistor, junction transistor. Whereas, next you can go for the current equation of a MOSFET. There, the currents are not due to the law of junction. There, it is not a junction device. It is a channel. It is a square law. The principle what we use to go with the MOSFET currents are square law. That's why we call them as a square law devices. Square law devices. Excuse me, right, dear students? So, what else we studied? Just recollect, guys. So, the first one, this for notes purpose here, because you're very near to the exam. As I told you a number of times, not the place to do research. It is the time to recollect. Time to recollect what we have studied. An overview. It's a revision series. Right, dear? So go with the first point. So drift transport, diffusion transport, tunneling transport, thermoelectric transport. Just recollect from your entire syllabus of carrier transport. The second is drift. As I told you, in drift, two important major parts you need to understand, that is mobility, and second is what here? Conductivity. Whereas the third is equilibrium, concentration of carriers, and the fourth, concentration of carriers under equilibrium, or we say non-equilibrium. So under non-equilibrium, if you consider, you have a concept of low level injection. Then I believe you remembered, one is continuity equation, the concentration of carriers changing with respect to time, with respect to spatial distance or spatial charges, right? And you have bipolar transport. Bipolar transport, that is a beautiful equation we have. We can solve a lot of questions. We have solved already in the class, and a lot of previous gate questions you have. And diode, BJT current equations. And in BJT, you have the current equation, let me say, in the forward active, which is very important for amplification purpose in analog circuits, forward active. Then you have a current equation in the collector with early voltage, without early voltage, early effect, lambda. Lambda is equals to 1 by VA, where lambda, base width modulation parameter. Whereas in case of MOSFET, what is lambda? Channel length modulation parameter, right? Yes. Whereas in the similar way, you have continuity equation, bipolar transport equations, if you want to just think about current equations, okay? And you have MOSFET current equations, as I discussed already. And optoelectronic currents, you have photodiodes, you have solar cell. In the solar cell, you have open circuited voltage, short circuited current. Product of both is the power which the solar cell is delivering to the load. Thus, power reaching to the load is a maximum power, which is PM, which is nothing but VM into IM. So, if you want to find the maximum power, then we are supposed to find the power, then differentiate that power with respect to voltage equals to 0, you'll be getting one expression. Or differentiate that with respect to current, if it is equal to 0, you'll be getting current. So, product of both, you'll be getting maximum power. Guys, correct or not, dear students, right? So, you have a wonderful picture here. Then last but not least of the entire syllabus is capacitance of diode. Just electronic devices, divide into only 4 steps, please. Okay, capacitance of a device. Discuss number of times. Whenever a space charge region exists, we have the capacitance. So it may be a PN junction diode, it may be a BJT. BJT has 2 junctions. Every junction has a space charge region. Because of that, it has a capacitance. MOSFET, my God, in MOSFET, a huge capacitance impact will be there. I hope you remembered. One is what here? MOS diode capacitance, or we say MOS capacitance. In that we have accumulation mode of operation. In that, depletion mode of operation, inversion mode of operation. In inversion, we have a weak inversion, we have a strong inversion. In that, low frequency and that high frequency. Correct or not, dear students, right? How many capacitances are showing impact? We have discussed a lot of things we discussed. Not only that, in MOSFET, you have body to the source, junction capacitance, body to the drain, junction capacitance. Not only that, one problem in the fabrication is nothing but overlapping. So, the metal to the body or metal to the source, overlapping capacitance, metal to the drain, overlapping capacitance, and that overlapping is not at all advisable because of the huge extra capacitance impact is acting on the body, which reduce the higher frequency operation, which increase the time delay, right? Transit time, which is not advisable, right? That's the reason why what we have done, polysilicon, N plus polysilicon or a P plus polysilicon we have used. Instead of using aluminum or copper, metals, we commonly used degenerated, polysilicon materials. Excuse me, correct or not, dear students, right? So like that, we have capacitance impact. So if you check it out carefully, guys, the very first is junction or a transition capacitance. Transition capacitance is also called as depletion capacitance. Hope you know that. Then we have the second part, charge storage capacitance, or we say diffusion capacitance. And a third, diode or a bipolar junction capacitance, yes, which is very important. Hope you remembered all the formulas, right? In the similar way, we have a transit time, time delay, switching speed. Yes, if I want to find that, I need a capacitance, know the choice I have. And in the similar way, you have a MOS diode or MOS capacitance, and this is important, man, CV characteristics, correct or not? It may be a diode has a CV characteristics, and a MOS diode, which is so called as a MOS capacitance, have a CV characteristics. Just now we discussed high frequency response as well as low frequency response, right? In the similar way, MOSFET capacitance, like overlapping capacitance, whatnot. So the entire syllabus, it is simply classified into 4. Okay, dear students. So I'm just recollecting. Have a look carefully. Just have a look onto the screen. The first is the entire syllabus. The first, is electric field profile, and the second you have energy band diagram, and the third you have carrier transport and current equations, and fourth we have capacitance of the device. Is it okay? So let us enter into more deep, let us dig deeper, okay? By that you can recollect the things, and I'll be discussing the overview of the entire syllabus, individual concepts in the entire syllabus in the given time what we have. Then we'll be doing some numericals, okay? I mean to say, after completion of a specific topic, in what way you can expect questions in the GATE exam, I'll be discussing those questions. So instead of discussing the previous GATE questions, because we have solved a lot in the class itself, the previous GATE questions, by now you have been solved a lot of PYQs, previous GATE questions. Already, again solving previous GATE questions, I don't think so. That is, that is a good sign for me, okay? That's the reason why I'm expecting some sort of tricky questions from different resources and sources, okay, from IIT, standards. Based on that, I'll be doing those example numericals here. I believe that will be a practice for you. That will give you a lot of conviction. Okay, my dear students, everybody. And any tricky questions in the previous GATE, I'll be solving those also. Tricky questions, that means a student, common student, they may not get an idea, okay, we can solve in this way. Those questions I have been selected, I'll be doing those questions also. Right, my dear students. The very first, electric field profiles, as I discussed, that is what the first topic we are starting right now. Okay, I need high concentration, have a look carefully. Students, electric field profile, you know that the very first thing is we have two types of doping profiles. We have two different types of doping profiles. One is step graded, second is a linear graded. Correct or not, dear students? Step graded, second is what here? Linear graded. So here, from here, what you're supposed to understand. Excuse me, please tell me, what is electric field here? Electric field, I hope you know, electric field is strictly depends on 1 by epsilon. Am I right here? Electric field strictly depends on what here? 1 by epsilon, which is very important. Epsilon is equals to epsilon naught, epsilon r. So what is epsilon? Which is nothing but epsilon naught, epsilon r. What is epsilon r? Epsilon r, let me go for silicon. If it is silicon, it is 11.7, and if it is germanium, it is like 16, I believe. Okay. If it is gallium arsenide, gas, or gallium arsenide, 13.1, and if it is a silicon dioxide, it is 3.9. These values you are supposed to remember. Examiner may not give. If examiner provide this data, you're so lucky. Fix it. They don't provide this data, and accordingly you please follow. So these are all the default values what we have for epsilon r. So higher the epsilon, lesser will be the electric field. That is the very first important thing you should understand. Higher the epsilon, lesser will be the electric field profile. Correct or not, dear students, right? Then then go with the step graded diodes. If I go with the step graded, for example, let me say at equilibrium, I go under equilibrium. Is it okay, dear students? When I go under equilibrium, please let me know, N-type semiconductor contains what ions? Positive ions. Am I right here? Positive uncovered ions, or we say positive immobile ions. Whereas P-type semiconductor contains what ions? Negative ions. Uncovered ions or immobile ions. True or not, dear students, right? So accordingly, from here, you're supposed to go for volumetric space charge density, or we say simply space charge density. Then we should go for electric field profile, and you're supposed to go for the voltage profile. This is what the very first thing I discussed. Just recollect it, okay? So positive charges you can understand, and it is the step graded. It is not a linear graded. It is a step graded. Excuse me, correct? Whenever I say step graded, it must be a constant doping. Doping will not change with respect to time. So if you think about step graded, the doping, the doping dnd by dx will be equal to 0. That means with respect to distance, doping concentration will not change. In the similar way, dNA by dx must be equal to 0. So with respect to distance, the doping concentration should not change. Whereas here, there exists dNd by dx, there exists dNA by dx. The doping concentration, it is changing with respect to the distance. That is so called as the linear graded, whereas here it is a step graded. But this is a default type of doping what we say, and it is also called as abrupt junction. Am I right here? Abrupt junction. So default, maybe a diode, maybe a clipper, maybe a clamper, and most of the cases amplifier, BJT, and a MOSFET amplifiers, whatnot. Most of the cases, most of the default applications, we are using step graded. Specific applications like a voltage variable capacitors, like a varactor diode, for those type of special purpose or a specific application, we are going for linear doping. Hope you recollect it right here. And A strictly depends what here? Slope. It defines what here? Slope. And right, so from here, what is the volumetric charge density? If I go for a step graded diodes, so no doubt here, it's a neutral region. It is also neutral region. So this is positive, and here you'll be getting what here? Negative charge up to here. And no doubt this is representing what here? Xn, depletion width of N side, and this is representing what here? Xp, depletion width of a P side, and this is strictly representing W. What is W? Total depletion width. Okay, so a lot of previous questions you have based on that, you please try to recollect that. Okay, dear students, here it is a neutral region, so no charge, neutral region, no charge. Clear? And for example, I say up to how much distance we have the charge. If you ask me, q times nd plus into xn, q times nd plus into xn. This is called as what here? Areal charge density in the n side. And what is the nd plus? Ionized donor impurity. What is Na minus? Ionized acceptor impurity. Correct or not, dear students, right? And q times nd plus into xn, which is so called as qn dash. Coulombs per centimeter square. Charge per area, coulombs per centimeter square. This is nothing but areal charge density. In the similar way, q times Na minus into xp, which is nothing but qp dash. And you know that the entire body is electrically neutral. The entire, because it is fabricated on a simple semiconductor, silicon semiconductor on a single layer. So basically it is an electrically neutral, charge neutral. In that case, both charges can be equal. So Qn, which is equals to Qp, or then you'll be getting what here? Nd plus into Xn is equals to Na minus into Xp. So I'm happy to say, Nd inversely proportional to Xn, or Nd plus inversely proportional to Xn. What exactly it shows? Higher the doping, lesser the depletion width. Higher the doping, lesser the depletion width. So if I want to get this beautiful picture, I need the charge density profile, which is very important. And the second is what here? Electric field profile. What it says, electric field profile, just before I discussed, electric field is nothing but minus del V, where del square V is nothing but minus rho V by epsilon by Poisson's equation. Therefore, electric field is simply equals to integration rho V by epsilon dx. Wow. So integration of that, that's what I discussed before, right? Integration of that, you'll be getting this electric field. So what I'm going to get exactly here, dear students, you'll be getting like a simple triangle wave. And here, this is minus xn, this is xp. And this portion is nothing but max electric field. Maximum electric field. So previous questions, they have asked clearly at the PN junction or in the entire diode or a BJT or a MOSFET, maximum electric field exists where? Answer is only at the junction. And if I move away from the junction, electric field will be getting decreased. Electric field will be getting what here? Decreased. So what is maximum electric field formula? Have remembered? Emax is nothing but Q Nd Xn by epsilon. If you want to take, you can take magnitude, okay? Whereas the maximum electric field with respect to P side, Q N A Xp by epsilon. Q Nd Xn by epsilon, that is with respect to N side, Q N A Xp by epsilon with respect to what here? P side, that's it. So electric field changing with respect to distance. Second is maximum electric field. And from this electric field profile, you'll be getting what here? Voltage profile. So what is that voltage profile? So you know that, what is electric field? Is minus del V, which is nothing but minus dV by dx. If it is one dimension, if I go minus dV by dx, then what is voltage? Is nothing but minus integration electric field dx. That's it, man. That means integrating this, you'll be getting a voltage profile. So if I go for integration, it is like a curvature. You'll be getting like this. Am I right here? And this height is nothing but a contact potential, or we say contact voltage. And therefore, this portion, this is N type, so it is voltage at N side. And from here, it is a voltage at P side. So voltage at N side, voltage at P side, together you will be getting what here? Contact potential. Integration of a triangle, it is like a curvature. Excuse me, right, dear students? So like that, we have, charge density profile, electric field profile, as well as what here, voltage profile. Hope you recollected. In the similar way, what is maximum electric field? Just now we discussed. They are the important formulas. So E max, just now we got, which is E max. Nothing but what here, Q ND Xn by epsilon. This is, these are all the questions for you. These are all the questions for you. Okay, and doping versus depletion width. What are the formulas? Just recollect. You recollect yourself. From your side, you please recollect. Here I'll be writing the formulas. From yourself, you recollect. I may not hear your voice. Okay, but you just think those formulas clearly. Here I'll be writing that. Okay, so doping versus depletion width. Xn, depletion width on n side. What is that? Under root. What I'm going to get? 2 epsilon by q into 1 by Na plus Nd into Na by Nd into contact potential. Am I right here? Or into built-in voltage. In the similar way, what is Xp? Xp is equals to, what is that? 2 epsilon by q into 1 by Na plus Nd into Nd by Na into built-in voltage. Because it is Xp. In the denominator, Na must be there. Higher the doping, lesser the depletion width. In the similar way, what is the total depletion width? Which is nothing but Xn plus Xp equals to what, dear students? So, what I'm going to get? 2 epsilon by q into 1 by Na plus 1 by Nd into contact voltage, or we say built-in potential. That is, what is built-in potential? Junction potential. See, this is junction voltage is equal to built-in voltage at open switch. At open switch, because equilibrium indicates what here? Open switch. Okay, maybe a contact voltage, maybe a junction voltage. I hope your formulas are correct. I hope you recollected. Okay, so you got the correct answer. Okay, dear students, good. What is next? In the gate exam, this is very important. Some of the previous questions, if you check it out, they're asking in the gate exam, if Xn or Xp is given, they're giving either Xn or Xp. Now we are supposed to find the total depletion width. That means here Xn is given or Xp is given. Now the examiner is asking to find the total depletion width. Then what should I do? Simple logic here. Don't do research in the exam. Okay, just divide both. For example, I know Xn, I need to find W. Divide both. You'll get some expression. If I divide both and if I could solve, you'll be getting like this. For example, Xn by W, Na by Na plus Nd. In the similar way, Xp by W, simple logic. So exactly opposite, Nd by Na plus Nd. I'm not asking you to mug up these formulas. My request is, don't mug up. If you mug up, you'll be getting overlapping. Because gate exam, syllabus is not only electronic devices. If only one subject you have in the entire gate exam, that is interesting. But in the gate exam, it is mixed with multiple subjects: control systems, network analysis, communication, electronic devices, analog electronic circuits, network analysis, correct or not, is electromagnetic transmission lines, mathematics, aptitude, whatnot. So 10 subjects you have, you need to mix it all. So my request is, understand the logic behind this instead of mugging up the concept, okay? So guys, Xn, I know the individual, formulae. W, I know the formulae. Just divide both, you'll be getting one expression. Xp by W, you'll be getting one expression. By that, you can easily solve the numericals there. Maybe you may take just 40 seconds or 50 seconds to produce these formulas. That is enough. 40, 50 seconds delay is fine, but you're getting an accurate answer, which is very important.